Hello guys, can you hear me? Good evening. Yes, so we'll wait for a few more minutes. Okay. Uh, for others, and then we'll start. Okay. So 5 minutes we have. Semester exam or something? Is it? Okay. When it is, Shraddha? Okay. Day after. Which subject? Okay. Chemistry. When is chemistry, guys? What is the portion for that? Syllabus for chemistry exam. Till chemical bonding, is it? Achha, states of matter is there. Atomic structure. Okay. Thermodynamics is also there. Okay. Got it. Got it. Got it. Okay. So I think almost half of the 11th grade chemistry is there. Yes, so everything in physical chemistry except the equilibrium chapter, right? Yeah. Anyway, not an issue. So guys, let's start with the session. I think last class we could not have the last class. Okay, so I'll plan to have a compulsory class for that. Okay, we'll do that. So last class we stopped at hybridization, right? We discussed how the VBT valence bond theory could not explain the bonding of CH4, right? And then I said that we got a new theory, and that is hybridization. So today in the session, we are going to start what is hybridization and how to find out hybridization. Okay. Okay. So let's start this. Still, I think there are many more students joining. Okay. We'll wait, guys, 2 more minutes, okay? Because I can see there are only 28 participants till now. Okay, so let me drop a message. Okay, fine. We'll start now. So we'll start with hybridization. So what is hybridization? Hybridization is the intermixing of orbitals. Okay. So first of all, you write down hybridization is the intermixing of orbitals. Intermixing of orbitals, orbitals of same atom. Orbitals of same atom. Okay. It is also the redistribution of energy. Redistribution of energy. So what happens in this, in some of the molecules, before the bonding, the atomic orbitals of one particular atom, okay, combines together and forms hybrid orbitals. Okay, that's why we are saying it as intermixing of orbitals. The orbitals intermix, combines together. Okay, they overlap, combines together, and forms a new set of orbitals. This new set of orbitals is called hybrid orbitals, and this entire phenomenon is hybridization, right? So by mixing of orbitals, there is redistribution of energy, right? And intermixing of orbitals, also the same thing. Okay. So write down hybridization is the hybridization is the process of hybridization is the process of intermixing of atomic orbitals of the central atom. I'll write down here. It is the process of intermixing of orbitals of central atom. Central atom. Write down, through hybridization, the energy is redistributed and new orbitals formed orbital forms, which is called hybrid orbitals, right? Which is called hybrid orbitals. Okay, all hybrid orbitals have same shape or similar shape and energy. All hybrid orbitals must have the same energy. One more thing here, the number of atomic orbitals combines equal number of hybrid orbital forms. Equal number of hybrid orbital forms. Copy this down. Suppose 2 atomic orbitals combines, so 2 hybrid orbital forms. 3, then 3 hybrid orbitals. 4 atomic orbitals, then 4 hybrid orbitals, and so on. Okay, we have to discuss one more concept in this chapter, that is molecular orbital theory. Right, so there is a basic difference between molecular orbital and hybrid orbital. Hybrid orbital forms when the orbitals of same atoms combines, okay, or intermix. Orbitals of same atom. But in molecular orbital, we have orbitals of different atoms. So that's the basic difference we have. So this point, did you copy this down, all of you? Yes. Next, write down. One side you write down orbital mixed. This table you draw. This is hybrid orbital. Okay. So what happens, suppose when S and P orbital mix, obviously of the same atom, right, forms 2 sp hybridized hybrid orbitals. Okay, when S and 2p mix, 3 atomic orbitals are mixing, so we'll get 3 sp2 hybridized hybrid orbitals. When S is mixed with 3p orbitals, then we get 4 sp3 hybridized hybrid orbitals. When X mixed with 3p and 1d, then the hybrid orbital forms number is 5 and the hybrid orbital is sp3d. If it is 1s, 3p and 2d, then the hybrid orbital forms are 6 sp3d. So this is the hybridization we have based on the number of atomic orbitals combines. All of you copy this down. Don't leave this. Okay. Yes, DSP2 is also possible. That is square planar geometry. In this chapter, you don't have use of that. If you want to write, you can write it down. 1 d orbital, right? 1 s orbital and 2 p orbital. This gives you 2, 3, 4 dsp2 hybridized hybrid orbital. Even d2 sp3 is also possible, right? This kind of geometry and hybridization you will get in grade 12 when we study coordination compound. Done? Yeah. Okay, so this is the thing. Now there are a few characteristics of hybrid orbital you must remember. Okay, a few points I have given you already. You can continue in this also. Next, write down I have given you already all hybrid orbitals must have the same energy, right? Next, write down like atomic orbitals, like atomic orbitals hybrid orbital can also accommodate maximum 2 electrons. Means in one hybrid orbitals, we can have maximum 2 electrons like we had in atomic orbitals. Now this point is very important, this one. Like hybrid orbitals forms only sigma bond and may contain lone pair and may contain lone pair. If you remember in organic chemistry, right, we had discussed a bit of hybridization and I told you that we'll see this in chemical bonding chapter. If you look at this structure and if I find out the hybridization of each carbon atom here, right, if you remember I have told you that we just need to count, one more thing I'll do. 2, 3, C double bond O, NH2. Okay, one lone pair on nitrogen. So if I have to find out the hybridization, this one I have done already in organic chemistry, if you remember. I told you that you just count the number of sigma bond and lone pair. Okay, like you see, for all these carbon atom, we have one hydrogen attached, right? One hydrogen here, one hydrogen here. And there is no lone pair on these carbon atom. Could you tell me how many sigma bond we have here? This one we have done, right? How many sigma we have of this carbon atom? Could you tell me? How many sigma bond? 3 sigma bond. Do we have any lone pair on the carbon atom? Do we have any lone pair on the carbon atom? No, right? That's why the hybridization is what? This carbon is sp2 hybridized because it's 3 sigma bond. Have we done this kind of question in organic chemistry? If you remember? All please respond. We have done this, right? So here you can understand the reason that why we are counting only sigma bond and lone pair. Okay, yeah, you can understand the reason here why we are counting only sigma bond and lone pair. So reason is what? Because the hybrid orbital that forms, this hybrid orbital forms only sigma bond. It can never form pi bond here and it may contain lone pair. This is the property of hybrid orbital. Okay, we'll discuss more examples into this one. But for just for this reference, if I ask you to to find out the hybridization of each carbon atom here, all the carbon atom in the ring is sp2 hybridized, yes or no? Is sp2. This carbon is also sp2 hybridized. Okay. If you look at this carbon is sp3. This carbon is sp2 because we have 3 sigma bond. This carbon has 3 sigma bond, sp2. This carbon has 3 sigma bond, sp2. This nitrogen has 3 sigma bond and 1 lone pair. So it is sp3. Any doubt in this? You can tell me, all of you. Any doubt in this? Right, so we haven't done anything new over here. We have already discussed all these things. Okay, the example just I have given you here so that we can understand that why we were counting only sigma bond and lone pair if the structure is given in order to find out the hybridization of each atom. Okay, remember it is hybridization for one atom, means this carbon atom or this carbon atom or this carbon atom. Hybridization is not defined for molecule. Okay, keep that in mind. Okay. Now the next, property here you write down. If there are pi bonds to be formed, then equal number of atomic orbitals must be left unhybridized. Okay, next one is the last one. Geometry of the molecule can be determined by knowing the hybridization. It's very simple to find out hybridization, but if you want to understand the actual thing, you have to give a little bit of time here. Okay, I can finish this hybridization in 2 minutes. 2 more minutes, I'll be able to finish this. Okay, but I'm not giving you just a small short trick we have here, which we use in solving questions. But I want you to understand the actual concept, and then we'll see the trick. Okay, so first we'll discuss the actual concept. See here what happens. According to the hybridization, we can find out the geometry. So if hybridization is sp, geometry is linear. If hybridization is sp2, geometry is trigonal, planar. sp3, geometry is tetrahedral, right? sp3d, then the geometry is trigonal bipyramidal, TBP. sp3d2, geometry is octahedral, and octahedral is nothing but same as square bipyramid. Done? Okay, now you see the shape of the hybrid orbital. You don't have to memorize this, but just if S and P combines, or if P and P also combines atomic orbitals, the hybrid orbital that we get is this one. This is the hybrid orbitals we get when the atomic orbitals combines. Yeah, pentagonal bipyramidal, if you ask me, it is sp3 d3. The geometry is pentagonal bipyramidal. Not very important, but you'll get rarely this sp3d3. Okay, so this is hybrid orbitals, and these are atomic orbitals of same atom, obviously. Atomic orbitals of same atom. Okay, now we'll try to understand how this hybridization explains the geometry, the bonding of CH4. Because of that only we have this particular theory of hybridization. Geometry of DsP2 is square planar, Ruchita. DsP2 geometry, if you want to write down, DsP2 is a square planar. Okay, you won't get this particular thing in this particular chapter, but yes, if you want to write, you can write it down. DsP2 is square planar. Okay, now look at this example of CH4. Because of this only we got this new concept, right, of hybridization. CH4 molecule, you see carbon has 6 electrons, and when you draw the electronic configuration 1s2, 2s2, 2p2, if you look at this orbital diagram, 2s orbital has 2 electrons and 2p also has 2 electrons. Okay, so 2 electron here and 1 here, 1 here. This is the distribution of energy in ground state. This is in ground state. But since this carbon is attached with 4 hydrogen atoms, it means we must require 4 unpaired electrons. So in order to get 4 unpaired electrons, this 2 electron of this orbital, it jumps into the vacant orbital of p, and we get here 1 electron and 3 electrons we get here. 1, 2, and 3. Okay. Now this has 1 s orbital and 3 p orbital here, right? Before it make a bond with hydrogen, this 4 orbitals, 1 s and 3 p, goes under hybridization. All these 4 atomic orbitals mix together and forms a new set of orbitals. So how many orbitals we get here? Could you tell me? How many orbitals we get here? Four, yes. Because 4 atomic orbitals combines, so we'll get 4 hybrid orbitals. Each hybrid orbitals has 1 electron, because here also we had 1 electron present. Okay, so this is sp3 hybridized hybrid orbitals. Then what happens? The 4 s orbital of hydrogen make a bond with this sp3 hybridized orbital, and we get the CH4 molecule. So if you look at this structure here, we have 4 sp3 hybridized orbital. So the structure is this. sp hybridized orbital is this 1, 2, 3, and 4. Right? 4 sp3 hybridized orbital of this thing, carbon, which has 1 electron each, as it is written here, 1 electron each. Now with this 1 electron, the s orbital of hydrogen overlaps and makes a bond. right? This is the s orbital of hydrogen. All these are s orbitals. 1, 2, 3. Oh, just a second. This is hydrogen. This is hydrogen. This is hydrogen, and this is hydrogen. S orbital. What is this overlap? Could you tell me? This overlap is sp3 s overlap. And in fact, we have 4 such overlaps possible present here, right? Everywhere we have sp3 s overlap. Okay, and that is how the bond forms in CH4 molecule. So what happens here? You see, these 4 bonds are formed by the overlapping of sp3 and s orbitals. Hence, all 4 bonds are identical and same. And that is how it explains the property of CH4 and hybridization of CH4. Did you get it? No doubt. So this is the theory of hybridization. Now, if you look at this, one more example. All of you have done that? Suppose we have BeCl2. Hybridization we need to find out. Okay. So beryllium, it is 1s2, 2s2. Right, and the 2p orbital is vacant here. There's no electron present in this 2p. So if I draw the diagram here, this is 2s and this is 2p. Okay, 2s has 2 electron and there's no electron in 2p. But it has to bond with 2 chlorine atom, means 2 unpaired electron for beryllium is required. So in excited state, what happens? One of the electron from 2s of beryllium, it jumps into 2p, and in excited state, the structure is this. 2s has 1 electron and 2p has only 1 electron. Okay, now before bonding with chlorine, this s and this p orbital, which has unpaired electron, these 2 intermix and forms a new set of orbitals, which we call it as hybrid orbitals, this one, right? And these 2 orbitals will be left unhybridized. Okay, 2p orbitals, write down here, 2p orbitals are left unhybridized. And these 2 orbitals, the hybrid orbitals sp, because sp and s and p combines, has 1 electron each as it was here. Okay. Now, when you draw the structure of this, obviously BeCl2, the hybrid orbital is this, and chlorine, the electron is present. This one has 1 electron, this one has 1 electron, and the chlorine, the electron is present in p subshell. So p subshell is this for chlorine. P orbital, in fact, is this for chlorine, which has 1 electron each. Okay, so this overlaps here and forms a bond along this line. So it's a sigma bond, right? This sigma overlap and this sigma overlap. Okay, so hybridization for D is this sp in this molecule. Yeah, if possible, then they can form pi bonds. Prakul. Here it is not forming, but in other cases, if it is possible to form, then they will form pi bonds. Tell me, did you get it, all of you? Okay. Now we'll take one more example. You will have a better clarity of this. Let's take an example of CO2 molecule. Could you tell me the hybridization of carbon in this? Okay. Okay, Prakul, I got your answer. Others, tell me the answer. No, Gayatri, that's not correct. Rohan, that's not correct. No, Stuti, it's not correct. Is it done in the class, like school class? Yes, Prakul, right. Ruchita, that's correct. Yes, Rohan, that's correct. See, it's very simple. Carbon has 6 electrons. So it is 1s2, 2s2, 2p2. Two electron, 2s, and one electron here. But in excited state, what happens? One electron from 2s, it jumps into 2p. And we get 4 unpaired electrons. So this one is ground state. And this is excited state. Okay. You know the structure of CO2? The structure of CO2 is O double bond, C double bond O. So if somebody asks you what is the hybridization of CO2, you can draw the structure and you can find the number of sigma bond and lone pair from the central atom. That is only 1 sigma here and 1 sigma here, 2 sigma and 0 pi. So it is sp hybridized carbon atom we have. That is what you can say directly, right? But why I have drawn this structure? Because there are 2 pi bonds, yes or no? Can hybrid orbital forms pi bond? No, right? But the central atom, carbon, has 2 pi bonds. Okay, it means out of this 4 orbitals here, 1, 2, 3, 4 of carbon, out of this 4 orbitals, 2 orbitals must be left unhybridized, right, in order to form a pi bond. So what we say that this S and this P in 1p goes under hybridization and it forms 2 electron and the 2 atomic orbital is this. So this one here you see, these are the hybrid orbitals, right, hybrid orbitals, and these 2 are the atomic orbitals. Atomic orbitals. right? So two pi bond we need to form here. The two atomic orbitals must be there unhybridized for the carbon atom. Now we'll draw the orbital diagram. But before that, we'll see the electronic configuration of oxygen also. It has 8 electron, 1s2, 2s2 and 2p4. 1s2, 2s2, 2p4, 2s is 2 electron and 2p4 has 4 electron. So 1, 2, 3 and 4. So what point I'm trying to make is, for oxygen there are 2 atomic orbitals which has 1 electron. That is what you need to keep in mind. Okay, this is 2s, here also 2s, here also 2p. This is also 2s, 2s, and this is 2p. Okay, so 2s and 2p orbital have 2 electrons unpaired for oxygen atom. This is for carbon. Now let us draw the orbital diagram. For carbon, there are 2 sp hybridized carbon atom, right? See here. sp hybridized carbon atom here and 2 atomic orbitals with one unpaired electron. Look at this. Wait. This is sp hybridized carbon atom of carbon. It has 2 p orbital also, atomic orbital. So one of the atomic orbital is this, right? And other atomic orbital is this. Okay, this is for carbon. All these orbitals has one electron. So here we have 1, here we have 1, here we have 1, and here we have 1. Okay. Now oxygen has 2 p orbitals which has one electron each. So one of the p orbital is this, and another p orbital is this, for example. Right, one p orbital is this, the another one is this for one oxygen atom, and this is the another one for another oxygen atom. Right, so this p orbital has 1 electron, this p orbital is 1 electron. Right, so all these orbitals has equal electron. Equal electron like this forms sigma here. Now when this forms here, 1 electron this side, 1 electron this side, when this forms a pi bond between, we have a sigma bond here and this atomic orbital. These are, if you look at the hybridization here, sp and p overlap, we have this side to form a sigma bond. sp and p overlap to form a sigma bond. Now to form a pi bond between carbon and oxygen, this 2 orbitals overlaps, right? It forms a pi bond, this 2 overlaps, and here also these 2 orbitals overlaps, and this 2 orbitals also overlaps, right? So what happens here, you see this middle one is carbon, this is oxygen with a single bond, this is a single bond we have, and we have a double bond here, which is this. This carbon has a single bond this side and a double bond here like this. So this is the structure. And for oxygen, you see it has 2 lone pair here. If you look at this 2s and 2p electrons are the lone pair on oxygen atom, and that you can place here. Did you understand this? You see the pi or bonds that is forming here. It is because of the overlap of atomic orbitals, not the hybrid orbitals. Okay, so I have started this thing, hybridization. Okay, till now you have to watch the video, you won't understand it now, right? But what I'm going to discuss after this, that you will understand. Guys, anyone has doubt in this? How sigma and pi bonds are formed? Please respond, all of you guys, quickly. Okay. Now the other thing is what you see, this kind of question, if you're going to solve in the exam, okay, this type, then it takes a lot of time, right? You have to draw a lot of structure and it takes a lot of time. So in the exam, we won't do questions like this, especially in the Chemon test or any competitive exam. If they ask you to find out the hybridization, they will either give you the structure, like I've given you the first one, okay, benzene ring and other things are there, like that, or they will give you the molecule, which we have here, right? So if a structure is given, fine, you can count the number of lone pair and sigma bond, right? But if molecule is given like this, CO2 and other molecules are there, then you have to, draw the orbital diagram like this, and then you see which orbitals are taking part in the reaction, which are not taking part in the reaction, and then you can choose the, uh, the orbitals which goes into overlaps, intermixing, and forms hybrid orbital here. This is what you need to do. Actual method is this, by which you can find out the hybridization. But like I said, this we won't follow in the test, right? Then what we should do? We are going to use the steric number rule in order to find out the hybridization. Okay, you see this. What is the steric number rule? It is a trick basically. Steric number rule. What is the steric number? Steric number is equals to what? In VSE PR, I have discussed what is steric number. It is a sum of bond pair plus lone pair. Yes or no? Sum of bond pair and lone pair. How to find out bond pair and lone pair? We calculate the valence electron. We'll divide it by 8. The quotient gives you bond pair and the remainder gives you number of electrons in the lone pair, right? That's why this is equals to Q plus R by 2. The same thing we have done in VSEPR, if you remember that. Yes, right? Now based on the steric number, you can say the hybridization of the molecule. Best method is this, steric number and hybridization. So if steric number is 2, hybridization is SP. If it is 3, it is SP2. If it is 4, then it is SP3. If it is 5, then it is SP3D. 6, SP3D2. This is the hybridization. Clear? Understood this? All of you have copied? Right? So if in the question, in the command test, they'll ask you to find out hybridization, we are going to use this method, steric number. But actual concept is this. Orbital overlap you need to check, and then you can find out the number of orbitals that take parts in the hybridization, and hence we can say the hybridization. Right? So steric number rule we are going to use. Find out the hybridization of hybridization of I3 minus NO3 minus XdO2F2 ClF3 also you can write IO2F2 minus. Try all these. Tell me the hybridization and geometry. Done, all of you? Okay. So for I3 minus, you see, we'll find out valence electron, and valence electron is 22. 7 into 3 plus 1 because 1 negative charge. Now, if you divide this 22 by 8, so we have 2 bond pair and the lone pair. So steric number is 5, hybridization is sp3d. Geometry is what? Geometry is TPP, yes. Shape is linear. Okay, Ritu? Shape is linear, geometry is TPP. NO3 minus, valence electron, is it 24? Yeah. So then 24 divided by 8, so we have 3 bond pair and 0 lone pair. So it is 3 sp3d. Sorry, it is 3, so it is sp2. Geometry is trigonal planar. Yes, geometry is trigonal planar. Next, XeO2F2, valence electron is it 34? So 34 by 8 gives you 4 bond pair and 2 lone pair. Sorry, 1 lone pair, 32 and yeah, 1 lone pair. And then we have 5 steric number. It is sp3d. Okay, TVP, the geometry here. This one is valence electron is 28. 28 divided by 8 is 3 BP and 2 LP, 5 sp3d. For this one, uh, 34, right? So 34 divided by 8, it's 4 BP and 1 LP, 5 sp3d. Any doubt in this? Yes, Rajita, 1 second. Okay. Rujita, do you have the notes for VSEPR? Have you written that table? Right? I want you to go back and look at this combination. For electron pair 5, this combination 2 and 3. What is the shape over there? Yeah, same only. Means with this particular thing, you can find out hybridization, you can find out geometry, you can find out shape. So everything, VSEPR, hybridization, VBT, it ends up over here. Any given molecule, if you have, okay, find out valence electron, divide it by 8, you will get bond pair and lone pair. That gives you the steric number, right? With the steric number, you can write down hybridization. Hybridization has a unique geometry, right? Depending upon the bond pair and lone pair, you have the idea of shape of the molecule also. Second one, NO3 minus it is. So nitrogen has 5 electron, oxygen has 6, right? 6 into 3, 18 plus 5, 23. And since negative charge is there, so 23 plus 1, 24. 24 divided by 8 is 3 bond pair and 0 lone pair. Steric number is 3, hybridization sp2. Yes, Prakul, understood. No, valence electron we need to take, so it should be 5. Any doubt, guys, in this? Are you finding it difficult or easy? Or moderate? Okay. Yeah, these are not much tough, okay? Once you practice a bit more, you will have the idea of it, how to do it. Okay. Now after this, what happens, if you look at the, if you look at the structure for oxygen molecule in VBT also, we have discussed this, that we have OO double bond and 2 lone pair on each oxygen atom. This is the structure of O2. So this is structure of O2 according to the valence bond theory. It suggests that oxygen molecule is diamagnetic in nature because all electrons are paired. Okay, when all electrons are paired, the molecule is said to be diamagnetic in nature, right? But experimentally, this observation was wrong. Okay, experimentally it has been observed that oxygen molecule is paramagnetic. Okay, so this thing was found out to be wrong. It's not correct. Actual thing is what? Oxygen molecule is paramagnetic in nature. This is correct. Okay. One second, guys. Just okay. So paramagnetic, right? So experimentally, this is found to be paramagnetic in nature, and but VBT suggests that O2 is diamagnetic. So again, there is a drawback in this theory, right? Because valence bond theory, yeah, once again, Srigori, right? Valence bond theory suggests, see, first of all, paramagnetic and diamagnetic, it is just a property of a molecule, okay? Paramagnetic molecules are those molecules which has unpaired electron, okay, which has unpaired electron. For example, if I write down NO2, how many electrons this has? 23. Odd number of electrons. It must has one unpaired electron only. So when unpaired electron present, the molecule is said to be paramagnetic. When all electrons are paired, for example, H2. H2 you see, there are only 2 electrons and these electrons are paired, right? Okay, it's paired. So it is diamagnetic molecule. This is what the simple definition of paramagnetic and diamagnetic molecule. Property is what? Paramagnetic molecule has unpaired electron, and when it is placed in the magnetic field, it is weakly attracted towards the magnetic field. Okay, so it experiences some force in presence of magnetic field or electric field. Force can be of attractive in nature or repulsive in nature, right? But if the molecule is diamagnetic, correct, then the molecule is diamagnetic, then there is no effect on this. Whether you place this in magnetic field or in electric field, it won't experience any force. It won't get deflected from its path. Okay. So this is what the definition of paramagnetic and diamagnetic molecule is. So what happens according to VBT, oxygen molecule is observed to be diamagnetic, but experimentally it has been proved that it is not diamagnetic, it is paramagnetic, because in presence of magnetic field, it gets attracted towards the magnetic field. Are you understanding this? Yes, correct. So obviously, again, this is the drawback or the flaw in VBT, valence bond theory. Now, to explain the magnetic property of oxygen, we got a new theory, and that we call it as molecular orbital theory. Okay, so heading, all of you write down. You should know why we need this particular theory. You should know why we need the theory of hybridization. Okay, so there was some drawback in VBT, which gives us hybridization, and again this molecular orbital theory. Did you understand? Yes, this the background of it. Did you understand Why we need this theory? Yeah. Okay. Now we see what is molecular orbital theory and how molecular orbital theory explains the magnetic behavior of oxygen. Okay. So what is molecular orbital theory first of all? You see, like in hybridization, atomic orbital combines and forms hybrid orbital. So here also in molecular orbital theory, orbitals of atoms combines and forms molecular orbital. So let me write down these 2 points, then probably you will understand then what is the difference in the two things. One basic difference we have here, write down, atomic orbitals. When I say atomic orbitals combines and it forms hybrid orbital. Hybrid orbital. Again, if I write down atomic orbitals, orbital combines and it forms molecular orbital. Okay. Then you'll ask me, so what is the difference in the two? Both you are saying atomic orbital combines and forms this. Then what is the difference between molecular orbital and hybrid orbital? Yes. Okay. So the basic difference is what? When hybrid orbital forms, then the atomic orbital must belongs to the same atom. This atomic orbitals, when it forms hybrid orbitals, this atomic orbitals belongs to the same atom. But when molecular orbital forms, atomic orbitals of different atoms combines. Are you getting me? Yes. Now you look. Now you go back and see this. The examples of CH4 I have discussed. 1 second. Yeah. The examples of CH4 I have discussed. You see this. BeCl2 CH4. Right. This, what I said, this 4 orbitals goes under hybridization, right? All these 4 orbitals of carbon, we don't have here orbitals of hydrogen, is it? Yes, no? The atomic orbitals of carbon combines and forms hybrid orbital. Okay, so only one atom is involved in this. If you look at this one, BeCl2, the atomic orbitals of beryllium combines and forms hybrid orbital. Okay, another one, atomic orbitals of carbon. You see this carbon orbital, right? So atomic orbitals of carbons combines and forms hybrid orbital. No, you see, we have here hybrid orbitals is forms when different orbitals of same elements combines. You see this, that's what I'm telling you, Shraddha. Different orbitals of same atoms combines, forms hybrid orbital. Molecular orbital, when we have orbitals of different atoms involved. Understood? Right? So all these examples that I've given you, you can easily understand that the atomic orbitals of same orbitals takes part and it forms hybrid orbitals. Different atoms of same element you can take. You can talk about isotopes here. Right. Rarely we cannot say it's not possible. Right. It's possible. Right. Yes, Shraddha. Got it. Understood. Okay. So first point is the difference between molecular orbital and hybrid orbital is in molecular orbital, we have different atoms involved in this, right? Now, 2-3 points to write down, and then I'll discuss the other things here. Write down the first point next year. In a molecule, electrons are considered to be associated with, in a molecule, electrons are considered to be associated with all the nuclei in the molecule. All the nuclei in the molecule. Next, write down. As electron in atoms occupy atomic orbitals, similarly, electrons in molecules as electrons in atoms occupy atomic orbitals. Similarly, electrons in molecules are present in molecular orbitals. Right? So the basic difference you must take care of. Other things are very much similar to that of hybrid orbitals. Okay, like the next point you write down. The number of molecular orbitals formed equals to the number of atomic orbital combines. Right? The number of molecular orbitals forms equals to the number of atomic orbital combines. Next, like atomic orbitals, molecular orbitals can also occupy, orbitals can also accommodate 2 electrons, maximum of 2 electrons. Right? Molecular orbitals can also accommodate maximum of 2 electrons. So we are talking about the combination of atomic orbitals. So there are 2 different ways for combining of atomic orbitals. So what I'll write down here, molecular orbitals, write down. Molecular orbitals forms by 2 different ways. The first one is linear combination. of atomic linear combination of atomic orbital, and the second one is united atom method. In this two, this is not in our syllabus, only we have to study linear combination of atomic orbital. Okay, now linear combination of atomic orbital is what? Heading you right down. Linear combination of atomic orbital. According to this, what happens when two atoms combines? When two atoms combines, forms a molecules. These atoms combines in two different ways. One possibility is what? Either they'll have the same phase. Psi A and psi B are the wave function of A and B, and psi AB is the wave function of AB. Right? So A and B atoms, either they will have same phase or opposite phase. Same or opposite phase. We are talking about the combination of orbitals of two different atoms, right? Orbitals are nothing but the path of electrons, so it must have some wave characteristics. That's why we are talking about wave function here. This part is not important. They won't ask you any questions on this in JEE also. Okay, but since it is there, we are just discussing it. You have to keep in mind, when A and B combines with the same phase, okay, then the molecular orbital that forms, we call it as bonding molecular orbital when the phases are same. Bonding molecular orbital. In short, we write it as BMO. When the phases are opposite, different, then it is anti-bonding molecular orbital. That is ABMO. Right, there is a formula we have of this combination. Psi AB is given as N is the normalizing factor, Ca is a constant, psi A plus Cb into psi B. Just write it down, you won't get any questions on this. Okay, it is there in the linear combination of atomic orbital, not much important. N is the normalizing factor. N is the normalizing factor. It just, ensures that the probability of finding an electron in the universe is 1, right? Normalizing factor. Ca and Cb are the factors to minimize energy. Ca and Cb are the factors to minimize energy. Okay, so next write down one note here. Yes, normalizing factors is the factor which ensures that the probability of finding an electron in the universe is 1. Okay, that is normalizing factor. Ca and Cb are the factors to minimize energy. Ca and Cb are the factors to minimize energy. Okay, yeah. Now you see this, how this molecular orbital forms in different combinations. Okay, shape I'm giving you here. Okay, just write it down. Hardly you will get questions on this. I have seen only one questions on the shape. That's why I'm giving you, but not much important. When you have SS combination, like I said, there are two possible combinations. One is same phase, other one is opposite phase. Suppose we have two s orbital. Okay, this combines with this, and both has the same phase, plus minus here, plus combines with plus and minus. Okay, so this is when same phase combines, this forms BMO, bonding molecular orbital, which has a shape like this, elliptical we can say, where we have positive charge here, slightly negative charge here, sigma. It is sigma bond it forms because along the internuclear axis, the combination is taking place. Right, along this axis. Similarly, if this is plus, this is minus, combines with minus and plus, then it forms anti-bonding, ABMO. ABMO, the shape is this. Here we have minus, here we have plus. And in between these two, we'll have a nodal plane. Important one is for PP combination. I'll do that, just you finish it first. Do you have any exam on Saturday? No, it's not static. The charges are not static, Prabhul. That's why there is no repulsion. It continuously moves, and it is not the charge first of all. Okay, these are the phases of the orbital. Plus and minus are not the charge here. Take care of that. Okay, no problem, Shraddha. We'll discuss that later. Let it be. Let it be. We'll discuss that later. Anyways, okay, Friday then the class is not possible. Let it be. Okay. If you have PP combination, on PP combination, they have asked one question that I have seen. That's why I'm giving. You just need to know the shape here. Three possibility we have because we have three orbitals here. This combines with this, right? Plus combines with plus, and it gives bonding molecular orbital, which is this, minus minus plus, and this is BMO along the internuclear axis, sigma BMO, bonding molecular orbital. But again, if you have this one, minus plus minus plus, then it is a nodal plane will have here. Achha, this is sigma only, no wait. It is sigma, so it will be like this. This is minus, this is plus, and this is also minus, and this is plus. Okay. It is ABMO. If you have pi combination here, plus, plus, minus, minus, same phase, plus combines with plus, so we'll have this, and we have electron cloud like this, negative sign. Okay, this is BMO again, because plus combines with plus. When plus combines with negative, okay, plus, minus, minus, plus, this is the nodal plane. Only one kind of question is possible in this structure, that which of this combination gives sigma molecular orbital or pi molecular orbital. One is this. Other type, which of this combination gives bonding molecular orbital or gives anti-bonding molecular orbital. That is it. You just need to know the shape here. See, one more thing here, when it is bonding molecular orbital, right, bonding molecular orbital is represented by sigma, and when it is anti-bonding, then it is sigma star. Means this star represents anti-bonding star. When there is no star, it is bonding. Okay, why sigma? Because it is along the internuclear axis, right? That is why it is sigma. So sigma is BMO, sigma star is ABMO, anti-bonding. Okay. Here also the similar thing here. This one is sigma BMO. This one is again along the internuclear axis. ABMO is sigma star. Right? This is pi because internuclear axis is this. So it is pi BMO, but this one is pi star anti-BMO. Done, all of you? Okay. Now to conclude this, what we can write, that when the atomic orbitals of two atoms combines, they combines in both ways. We cannot neglect the possibility of any one. Okay. atomic orbitals combines in both ways, means either they will form bonding molecular orbital or they will form, means they will form both bonding plus anti-bonding molecular orbital. We cannot ignore the possibility of forming any one of the kind of orbitals, right? Both orbital forms, right? Because the phase can be same or can be different also. So if suppose we have 1s combines with 1s, look at this. If 1s orbital combines with 1s, so s always gives you sigma. So we'll get sigma 1s and we get anti-bonding also sigma star 1s. Star means anti-bonding. If 2s combines with 2s, we again get sigma 2s plus sigma star 2s, anti-bonding. If it is 2px, 2pz, I'll take first. 2pz combines with 2pz, it is sigma 2pz plus sigma star 2pz. Okay. Then we have 2px plus 2py. One of the p orbitals already formed sigma. This will form pi. Okay, 2px from pi. So pi 2px and pi star 2px. If you have 2pz and 2pz, then it is pi 2pz plus pi star 2pz. Right? This forms sigma. We usually, anyone you can consider as sigma. X and Y also you can consider as sigma. Yes, that's what I'm talking about, Prabhu. Okay. Any one you can consider as sigma. I'm sorry, the last one is Y. Wait. This is Y. 1 second, Prabhu. Okay. So any one you can consider as, pi, and others are sigma and others are pi. Generally, we consider internuclear axis along z axis. That's why I have considered PZ forms sigma here. Right, Prakul? This is just the assumption we have. Okay, but if you write suppose pi 2pz plus pi star 2pz, you won't get the wrong answer. Okay, it is the assumption that the internuclear axis is along z axis. That's why the pz orbital forms sigma 1. Right? Usually what happens, the energy of bonding molecular orbital is lesser than the energy of anti-bonding molecular orbital. Right? So obviously you see, if the orbital combines and forms all these orbitals, right? All these orbitals, in the molecule we have all these orbitals present. Now when you distribute the electron in the orbitals like we do in electronic configuration, similarly here also you can distribute the electrons of the molecules in the molecular orbital. So since we have all these orbitals present, so here also we'll distribute the electrons according to the energy of the molecular orbital. Right? So we always start with bonding molecular orbital and then we'll go to anti-bonding molecular orbital. The energy order is experimental that you should memorize. Okay, but in general what we say that when you have this thing, the energy profile, if you see, for bonding and anti-bonding, suppose this is the energy axis we have, y-axis, and suppose 1s combines with 1s. So 1s when combines with 1s, it forms ABMO, and this also forms BMO, right? Since BMO has lower energy, so I'll write down BMO down and ABMO up. Similarly, you can also write down 2s combines with 2s. So it forms ABMO. BMO and other orbitals also you can write. Okay, so this is the energy profile we have. Like I said, the orbitals forms both antibonding and bonding. So you should know the overall energy of the orbital, the order you should know, and based on that you can distribute the electron from low to high energy. Okay, so if there are two possibilities here, if the total number of electrons equals to n, case 1, when n is less than equal to 14 electrons, less than equal to 14 electrons, then this energy order you should know, orbital energy order, and you will get questions from this only, the one that I am discussing now. This is only the most important part we have here. Other parts are there, that's why we have discussed, but not important. Okay, so what is the energy order you see? Sigma 1s is minimum, then we have sigma star 1s, then we have sigma 2s, sigma star 2s. After this we have pi 2py, pi 2py, then we have pi 2px, sigma 2pz, sigma 2pz, and then we have pi star 2py, pi star 2px, sigma star 2pz. This is the orbital energy order. This orbital, which I have written like this, are degenerate orbitals. This two and this two means equal energy orbitals. And when you distribute electrons in this, you have to follow Hund's rule. While distributing the electron, you have to follow Hund's rule. Is that fine? Done, guys? Yeah, wait. No, N2 is this only. Less than equal to 14, no. Nitrogen has 14 electrons. So for N2, this is the order we have. Okay. The second case we have for distribution of electron, when the number of electron n is greater than 40 but less than equal to 20. In this case, only one change you have to do here. Sigma 1s is minimum, sigma star 1s, sigma 2s, sigma star 2s, then we have sigma 2pz, pi 2py, pi 2px, then we have pi star 2py, pi star 2px, then sigma star 2pz. Okay, this is the order. Means this position we have interchanged, that is it. Here also we have same thing. These two are degenerate, these two are degenerate equal energy orbital, right? We follow Hund's rule here also. Okay, based on this, first of all, we'll try to find out the magnetic property of oxygen, O2 molecule, because that is why we have this, the entire thing. That is molecular orbital theory. It has 16 electron. So when you distribute 2, 4, and write down separately this one, okay, 6, 8, 10, 11, 12, Hund's rule, right? First one electron and then pairing, 11, 12, then we have 13, 14, 15, and 16. You see, since we have unpaired electron present in the orbital, that's why oxygen is paramagnetic. Means 2 unpaired electron paramagnetic with 2 unpaired electron. Understood? Okay, that is how the magnetic behavior of oxygen has been explained. Okay, now the next thing, and all these things are important, okay, for exam point of view. We can also calculate the bond order with respect to the molecule with the help of the molecular orbital theory. Okay, by the way, what is bond order? How do we define it? What is bond order? I have done this, tell me guys. It is a number of bond between the two atoms in a molecule. Okay, that is how we define. Number of bonds, it is always for the two atoms in a molecule. It is not for the entire molecule. Number of bonds present between the two atoms in a molecule. No, molecular orbital theory is not valid for more than 20. Okay, it is not given there. Now, if I take this molecule, which is CH3, CH double bond, CH single bond, CH3. Suppose this is carbon. Suppose this is the first carbon, the second, third, and fourth. If I ask you, what is the bond order of C1C2 carbon? What is your answer? Bond order of C1C2. 1, because there is only one bond present. C2C3, 2, and C3C4, it is again 1, right? So why this is 1? Because the number of bonds are 1 between the two carbon atoms. So first point is bond order we define between the two atoms in a molecule. Okay. I have also told you that this bond order may have the fractional value, right? This may have fractional value when resonance is possible, right? Fractional value. What I said, we can find out bond order with respect to the molecular orbital theory. Okay, let's see this. What is the bond order of nitrogen molecule? An N bond in nitrogen molecule. Tell me the bond order. Is it 3? Yes, 3. Could you cross verify? We can also cross verify this with molecular orbital theory. With the help of molecular orbital theory, we can find out bond order with this formula. The bond order for for this molecular orbital theory is number of electrons in BMO, bonding molecular orbital, minus number of electrons in ABMO, anti-bonding molecular orbital, and this is divided by 2. This is the formula we have for bond order according to molecular orbital theory. Now what I want you to use this formula and find out the bond order of N2, nitrogen molecule. How many electrons nitrogen has? The number of electrons for nitrogen? Equals to? No, it's 14. How it is 28 or 7? 7 electrons in one nitrogen atom. 7 electrons in one nitrogen atom. 14 is the atomic mass, right? So 14 is the total number of electrons for nitrogen. Follow the order of orbitals given. It is the first order it follows. Okay. And then find out bond order. What you are getting? Are you getting as 3? Yes, it should be 3, right? So I'll write down the order here. The order is sigma 1s, sigma 2s, sorry. Sigma 1s, sigma star 1s, then sigma 2s, sigma star 2s, pi 2p, x, pi 2p y, sigma 2p z, then pi star 2p y, pi star 2p x, sigma star 2p z. If it is more than 14, then this two you need to interchange. That is it. It has 14 electrons. So if I distribute 2, 4, 6, 8, 9, 10, 11, 12, 14. Okay. So bond order is the number of electrons in bonding molecular orbital, which is this, that is 6 plus 4, 10, minus 4 by 2, that is 3. Okay. That's why the bond order is 3. You can find out the bond order of hydrogen also. What you are getting from bond order of hydrogen? It has 2 electrons. So it is simply sigma 1s2 and there is no electron, right? So bond order is equals to 2 minus 0 by 2, that is 1. What is the bond order you are getting for He2? It has 4 electrons. Then we have sigma 1s2, sigma star 1s2. So bond order is what? 2 minus 2 by 2, that is 0. 0 means what? There is no bond present, right? 0 means what? Bond order is nothing but the number of bonds. So when the number of bonds is 0, then there is no bond between the helium atom. That's why you see helium exists as helium atom only. It does not form He2 like hydrogen. This is not possible. Are you getting it, guys? This is not possible. We can conclude this, it does not exist. Because there is no bond, it does not exist. Right? So the molecule for which the bond order is 0, right? Then the molecule does not exist. Yes, can say that. We can generalize this. If the bond order is 0, then the molecule does not exist. Correct, Arshit? Okay. Even on this, they have asked question in the exam. They'll give you 4 options and they'll ask you which one of these molecules does not exist. Okay. To find out bond order, if it is coming out to be 0, that is your answer. Any doubt till here? All of you, please respond. Is it clear? The point is, first 10 minutes, whatever we discussed in molecular orbital theory, okay, is not important. But when we start discussing this, the energy order, sigma 1s, sigma star 1s and all, and then this bond order, mostly 99% of the cases, they'll ask question from this portion only. Okay, must take care of that. Now, one more relation you see here. We know this relation we have discussed last class, that bond order is directly proportional to bond strength. And it is inversely proportional to bond length. So once you know bond order, right, you can also compare bond strength and bond length. Clear? One very important question, and most probably you're going to have this question in your school exam, and the question is compare the bond order, bond strength and bond length of O2 2 minus, O2 minus, O2 and O2 plus for these 4 molecules or ions. Okay. Yeah. So I'll do this for first one. See, O2 2 minus has 18 electrons. So order is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, pi 2px, pi 2py, pi star 2px, pi star 2py, and sigma star 2pz. We have 18 electrons, 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So bond order for O2 2 minus is, all these are bonding molecular orbital, right? 1, then 2, 3, 4, right? 3, 4, and 5, 5 into 2. We have 10 electrons in bonding molecular orbital minus 2, 4, and 4, 8 divided by 2, that is 1. Bond order is 1. For O2, 2 minus. Okay. Now, similarly, you can do if it is O2 minus, means it has 1 electron lesser, right? It means it has 17 electrons. So 1 electron that comes out from the anti-bonding orbital, right? Then it would be 10 minus 7 divided by 2, that is 1.5. Again, we have O2, it has 16 electrons. So bond order is 16 electrons. So bond order is, we have 10 minus 6 divided by 2, that is 2, and O2 plus has 15 electrons. So bond order is 10 minus 5 divided by 2, that is 2.5. Okay. So if I write down the order, which this question they have asked many times in NEET and others exam. Okay, so this is important here. So if I write down the order of bond order here, we have O2 2 minus, O2 minus, O2 and then O2 plus. If I go left to right, these three things. If I go left to right, O2 2 plus, the bond order increases. Bond order increases means bond strength also increases. Bond strength increases means bond length decreases, and hence the bond length increases from O2 plus to O2 minus. This is the order we have. Yes, O2 2 plus is 14 electron. So we'll consider the first one. Right, so this example is very important, the oxygen wala example. Many times they have asked this question in the exam, in school exam also, in competitive exam also. Okay, you must take care of all the three properties here. And when the bond order is 0, then the molecule does not exist. That is also very important. Okay, so this is it for molecular orbital theory. Any doubt in this? Any specific doubt? Okay. Next, write down what other types of molecule. NO2 we'll discuss in the last. It's a odd electron molecule. We'll discuss in the last. Wait. This are two types of bond we have, three electron bond and one electron bond. Odd electron molecule, we have just 2-3 examples. We'll discuss in the last. Let it be just now. Okay. Now the next type of bonding we have, we call it as hydrogen bonding. Write down, it is the electrostatic force of attraction. It is the electrostatic force of attraction between the hydrogen comma, attached to a more electronegative elements, between hydrogen attached to more electronegative element like fluorine, nitrogen, oxygen, etc. Yeah, I'll repeat it. It is the electrostatic force of attraction between hydrogen, comma, attached to more electronegative elements such as oxygen, nitrogen, fluorine, etc. and the another electronegative element. Done? Did you write this? Okay. Now, what do you mean by this? First of all, you see this example. What I said, when hydrogen is attached to an electronegative element, suppose we have M, right? M is highly electronegative. Mainly we have it fluorine, we can have it fluorine or nitrogen or oxygen or chlorine, etc. But mainly we define for fluorine, oxygen and nitrogen. Okay, because of the high electronegativity of these atoms here, this attracts the bond pair of electron towards this side, and after some time, the bond becomes polar. This atom will have delta negative charge, and this atom will have delta positive charge. It is very much similar to that I effect, if you remember, inductive effect. Okay, this happens. Now suppose if you have another electronegative element, suppose you have oxygen, hydrogen, and hydrogen. It is like this. Delta positive, and delta negative. Oxygen is also a highly electronegative element. Now when these two atoms comes closer, right, this electronegative atom and this hydrogen, then there will be an electrostatic force of attraction because of this delta positive and delta negative charge. There will be an electrostatic force of attraction. This electrostatic force of attraction is hydrogen bonding. Copy this down. Hello. Yeah. Yeah, okay. So hydrogen bonding, first of all, hydrogen involved, but hydrogen must be attached to the electronegative element. This must be electronegative. So it is a bond, electrostatic force of attraction between hydrogen and an electronegative element, first of all. But this hydrogen, which is involved in hydrogen bonding, must attached with an electronegative element. Understood this? So this hydrogen bonding is possible in a molecule like H2O. In water it is possible. In NH3 it is possible. In alcohol it is possible. HF, hydrogen fluoride, it is possible. So there are many examples for that. This happens because of the high electronegativity of the atoms attached to the hydrogen. Okay, if you look at the hydrogen bonding in water, all these molecules you see, this has delta positive, delta negative, delta positive charge, delta positive, delta negative, delta positive charge. Then we have delta negative, delta positive, delta positive, delta negative, positive, and positive, delta negative, positive, and positive. Okay, this kind of charge separation is there. Now, when these atoms comes closer, this oxygen and hydrogen will have a force of attraction, electrostatic force of attraction. This will have a force of attraction. This will have a force of attraction. This will have a force of attraction. All these force of attraction are hydrogen bonding. So water molecules are associated like this with other molecules, and hence this we also call it as an associated molecule, because all the molecules are connected with hydrogen bonding, hence it is associated. It is possible with two different molecules also. For example, you see we have H2O, right? and NH3. So nitrogen is delta negative, delta positive, right? And this is also delta positive. Sorry, delta negative, delta positive, delta positive, positive, and positive. Right, so these two will attract each other. This is the hydrogen bond, electrostatic attraction. Right, so it is possible between two different molecules also. More charge density on the atom, more will be the electrostatic attraction, and stronger the hydrogen bonding is. Right? So write down, as electronegativity increases, charge separation increases, and the strength of hydrogen bonding also increases. Done? No, hydration is something else. Hydration is something else. Hydration is like if you dissolve sugar crystal into water, that is also hydration. There's no hydrogen bonding between sugar crystal and this thing. What we say? Water molecule. Means you see, one thing you can understand here, obviously we cannot compare this with hydration because it's a different process, but there will be some kind of attraction. Hydration process is different. Means we have one concept here that we say the molecule which can form hydrogen bonding with water can dissolve in water. That we can say. Okay, but hydration process is different. Hydrogen bonding is different. It is possible that the molecule which shows hydrogen bonding with water get hydrated in water. That we can say. Understood? Okay. So this is the hydrogen bonding. The basic understanding you must have: more charge, more will be the electrostatic attraction, and hence the stronger the hydrogen bond is. Okay. Now this hydrogen bonding are of two different types, right? Next, write down types of hydrogen bonding. Two types of hydrogen bonding we have. Two types. The first one is intermolecular hydrogen bonding. right? If you see the name itself suggests that this is the hydrogen bonding between the two molecules of same and different type, like H2O and NH3 for example, right? That is intermolecular hydrogen bonding. Okay, write down. This type of bonding occurs this type of hydrogen bonding occurs when the hydrogen bond acceptor and the hydrogen bond donor are present in two different molecules. Or write down this way, wait. Are present in two molecules of same or different type. Two molecules of same or different type. See, hydrogen atom acceptor is what? The molecule which donates hydrogen for hydrogen bonding, means from which the hydrogen is involved. Like you see this one. In this particular example, this molecule is H atom donor, because its hydrogen is involved in hydrogen bonding, and this molecule is H atom acceptor. So when we have two different hydrogen atom donor and acceptor molecule, different or same also, in H2 also it is possible. This is also intermolecular hydrogen bonding, right? That is intermolecular hydrogen bonding. Write down between H2 and NH3. Example. Right, hydrogen bonding is this. The second type we have intramolecular. Hydrogen bonding. Write down. In this type of bonding, the hydrogen atom donor and acceptor, the hydrogen atom donor or acceptor are present in the same molecule. Look at this example. We have CH3, CH, double bond C, H, C double bond O, OH, and this is the bond we have. Within the molecule is here. This bond is H bond. Since it is within the molecule, so it is intramolecular, not intermolecular. It is intramolecular. Here also you can place any other atoms. CH3. This type of bonding is intramolecular bonding. Okay. Okay, this example you see, if you talk about, ortho, para and meta position, right? This is a benzene ring. And any group is attached. We can have OH, NH2, CHO, any group. With respect to this group, this position is ortho position. This position is meta position. And this position is para position. Right? This is also ortho. This is also meta. Meta, right? So in this particular, compound, any molecule of benzene, we have 2 ortho, 2 meta, and 1 para position. Okay, 2 ortho, 2 meta, and 1 para position. If you take the example of orthonitrophenol, right? Orthonitrophenol. So first of all, phenol is this, and orthonitro means what? At ortho position, we have NO2 attached, right? So at ortho, we have NO2 present, positive, negative. This is orthonitrophenol, right? When you talk about the paranitrophenol is this. OH, and here we have nitro group, O and double bond O, okay, and double bond O, and here we have a single bond and positive charge. This molecule is O nitrophenol. O stands for ortho. This is P nitrophenol. P stands for para here. So in orthonitrophenol, what happens? We have intramolecular hydrogen bonding possible. This is intramolecular H bonding. But in paranitrophenol, we don't have intramolecular hydrogen bonding, but here we have intermolecular hydrogen bonding possible. Look at this. Because this cannot make a bond with hydrogen because the distance is more over here. But if you have another molecule, similar molecule, paranitrophenol, if I place like this O and H, and we have NO2 here, NO minus, positive double bond O, and these two attracts each other because of the charge separation, delta positive and delta negative. Right, so this bond is again a hydrogen bonding, but it is intermolecular hydrogen bonding because it happens between the 2 molecules. The donor and the acceptor atom are present in 2 different molecules. Where I have taken O and N, Ruchita? Acha, I have, oh my god, is my bad guys, this, you corrected. This you corrected, my bad guys. It should be like this. O, H. Now it's right. Okay. So here we have delta negative, delta positive, delta negative, delta positive, delta positive, and delta positive, and delta positive. Clear? All of you have done, finished? Now, because of intermolecular hydrogen bonding, the boiling point increases. This is the property here, right? That's why the boiling point order, if I write down, for para-nitrophenol, the boiling point is more than to that of orthonitrophenol. This you must remember. Write down the heading. Properties. Just a second. We have 3 more points in this. We'll finish it and then we'll take a break. I'll take max to max 5 minutes. Okay, just max to max 5 minutes. Write down properties affected by hydrogen bonding. Just 3 points in this. That is it. First one, boiling point. Just now I said, write down, because of intermolecular hydrogen bonding, see, hydrogen bondings are the weak bonds. Okay, we don't talk about the stability because of hydrogen bonding, right? It won't affect the stability much. Okay, write down, because of intermolecular hydrogen bonding, the intermolecular force increases, hence boiling point increases. And hence the boiling point increases. Okay, this is the reason that H2O, the boiling point of H2O is more than to that of H2S, because in this we have intermolecular hydrogen bonding, H2S. Intermolecular hydrogen bonding, more boiling point. Same reason we have for NH3 also, more boiling point than PH3. In fact, this H2O, because of more boiling point, exists as a liquid, but this H2S exists in the gaseous form. And this question they ask in the exam also, that H2O exists as a liquid, but H2S as a gas. What is the reason? Okay. Second point, solubility in water. Write down the compounds which can form hydrogen bonding with water is soluble in water. The compound which can form hydrogen bond with water are soluble in water. Like you see, CH4, there's no electronegativity difference, can't form hydrogen bonding, is insoluble in water. But if you talk about alcohol, CH3OH, this is soluble in water. Okay. Third and the last point here is viscosity. Due to hydrogen bonding, viscosity increases. Due to hydrogen bonding, viscosity increases. Okay, this is it for hydrogen bonding. We'll have few more, 2-3 more points, topics we have to discuss. Small topics are there. Few examples we have that we'll discuss after the break. Okay. Take a break now. We'll resume at 6:50. Okay. Hello. Yeah. Shall we start, guys? Okay. See, there are a few small topics are left in this chapter. Okay. Miscellaneous topics we have here. I guess it does not have any connection with the previous thing that we have done. So we'll consider this under miscellaneous topics of chemical bonding. Okay. The first one we have bridge bond. Okay, heading you write down, all of you. Bridge bond. Bridge bond we have two types. You just need to keep the examples in mind. That is it. Okay. When you get the question, you'll understand that what you need to do here. Bridge bond, it's just a factual question you'll get. Two types of bond. The first one is 3 center two electron bond. And the other one is 3 center 4 electron bond. This we call it as a bridge bond. Okay, these two types of bond. What is 3 center 2 electron bond? Center means 3 nucleus. Center means here nucleus. Okay. The first example you see of 3 center 2 electron bond, and why we are calling it as 3 center 2 electron bond, that you will understand with this example. Keep this in mind that center means nucleus we have here. Take an example of BeH2. BeH2 goes under dimerization. Okay, it dimerizes and forms Be2H4. Dimerization means what? Two molecules combines together. That is dimerization. Okay. Polymerization, when we have more than 2 molecules combines, then it is polymerization. Okay. Now in BeH2 what happens, you see, on dimerization we get a stable structure, and that's why the dimerization possible. Obviously, logically you cannot understand that whether the dimerization is possible or not. That's why I said that it is a factual thing. You have to keep this in mind, that in this case the dimerization is possible and in other case it is not possible. Like this example you see, BeH2. Okay, so beryllium has vacant p orbital available in this bonding. If you look at the bond here, BeH, H, and another molecule is this BeH and H. If you look at the electronic configuration of beryllium, beryllium has 4 electrons, so it has 1s2, 2s2 and 2p0. There is no electron in p subshell, right? So in the excited state, what we can say, 2s has 1 and the another electron jumps into the 2p shell of this. So it is vacant p orbital, beryllium. And these two goes under hybridization, forms sp hybridized orbital, and these two are the vacant orbitals. So point I'm trying to make is, along with this bond, beryllium has vacant orbital, p orbital present here, right? Vacant p orbital present. So here what happens, this electron pair you see, the electron pair which is present in this bond and electron pair which is present in this bond. This electron pair is attracted towards this beryllium, goes into this vacant orbital, and this is attracted towards this beryllium. And that is how the dimerization takes place. So this converts into this molecule. Beryllium at the two corners, this hydrogen, beryllium, one hydrogen this side, one hydrogen this side, and here also we have H and B. This is the dimerized form of B2S6 here. Okay, now you see this forms a bridge here, right? This is a bridge between the two molecules. That's why it is bridge bond. Why we are calling it as 3-center 2-electron bond? I have given here 2 bonds, but the number of electrons are 2 only. It means that this 2 electron is associated with the nucleus of 2 beryllium atom and 1 hydrogen atom. Means this 2 electron is associated with this beryllium, this hydrogen, and this beryllium. So we have 3 nucleus, 1, 2, and 3, and 2 electrons. So it is 3-center and 2-electron bond. Understood? Right? So this bond is the bridge bond. We have 3-center. 3-center means 3 nucleus, 2 for beryllium, 1 for hydrogen, right? This bond is the terminal bond. Right? And this bond here this we call it as 3-center 2-electron bond. Yes? Done, guys? Three-center because we have 3 nucleus, right? And the 2 electron which was present here between this beryllium and hydrogen, now in this dimerized form, this 2 electron is associated with the 2 beryllium atom and 1 hydrogen atom, this 3 atom. That's why we have 3-center. 3-center means 3 nucleus and 2 electrons. Clear? So you have to memorize this, that in BeH2, we have 3-center 2-electron bond. Yeah. Yeah, I said no, Shraddha. See what happens. Beryllium BeH2 molecule is this. Now in this bonding state with two hydrogen atom, beryllium has vacant orbital available. Hence, it can accept the electron. Right? Correct. So this pair of electron, in order to get dimerized, this pair of electron is now associated with, like we can say, it donates to this orbital, or it is, associated with this nucleus, this hydrogen and this nucleus. 3 nucleus we have, and we get a bridge bond like this. It acts as a bridge between the two molecules. That's why the bond is bridge bond, and it has 3 nucleus, 1, 2 and 3. 3 nucleus, so 3 center, and since this 2 electron is distributed among the 3 atoms, hence it is 3 center 2 electron bond. Even this bond is also 3 center 2 electron bond. Yes, you are right, Gayatri. This bond is also 3 center 2 electron bond. You have to keep this in mind that in Be2H4, we have a bridge bond that is 3 centered 2 electron. Yeah. Okay. The another important example for this one, and in fact this one is more important, is for BH3. BH3 get dimerizes and converts into B2H6. Right? B2H6, diborane. B2H6 is diborane. Right? If you look at the bonding in BH3, electronic configuration of boron has 5 electron, 1s2, 2s2, 2p1. So in excited state, you see it must have 3 unpaired electron in order to make a bond with hydrogen. So excited state, you see 1 orbital is vacant here. So this one, boron has 1 vacant orbital. In fact, you can keep this in mind. Boron, whenever bonded with 3 bonds, it has 1 vacant orbital. And that's why this electron pair you see, which is present here, it is associated with this boron atom, and this electron pair also associated with this boron atom. And hence this 2 dimerizes and it converts into BH, B, hydrogen and hydrogen, hydrogen and hydrogen. Okay, this bond is 3 center 2 electron bond. Okay, so we have 3 center 2 electrons. This is bridge bond. And this is terminal bond. Terminal bond. We also call it as this one, we also call it as banana bond. Because this one, it looks like banana. That's why it is, nothing else. Right? And we have similar thing this side also. Right? So it looks like banana, hence we call it as banana bond. There are few properties on which they ask question in exam and that you should remember. And the first property is what of this? That is the bridge, the bond length if you see. If you take the bridge bond, boron hydrogen, the bond length of bridge bond is more than to that of terminal BH bond. Right? If you talk about bond strength, usually bond length and bond strength are opposite. But here still the bond strength is more for bridge bond, however, its length is more. Then terminal BH. So there's no mistake here. These two orders are correct. Bond length and bond strength. Usually it is inversely proportional, but here the same order we do not have because the two electrons are distributed among three centers, three nucleus. That's why we have greater attraction, and hence the bond strength of bridge bond is more than to that of terminal bond. No, it's not. We have two electrons only. Where we have the four electrons? It is three center, two electron. Okay, so these two property related to the bond length and bond strength, you must remember. Okay. Then guys, tell me. Yes. So another type of bridge bond we have, the second type, that is three center, four electron bond. We have two examples in this. The first one is BeCl2. In BeCl2, if you look at the structure, beryllium attached with one chlorine. Again, beryllium has vacant orbital. I'm not going to draw the electronic configuration again. We have discussed it in BeH2. Similar configuration we have here. Chlorine has three lone pairs on it. And we know beryllium has vacant p orbital that we have discussed already. So what happens, this chlorine donates its lone pair into the vacant orbital of this beryllium. And hence we get a bridge bond here, which is this BeCl, BeCl, Cl and Cl here. So one bond pair we'll have here, which is present as it is. Another one is of chlorine, and chlorine has two lone pairs here. Another one is of chlorine. This one, you see 1, 2, 3 center, 2 plus 2, 4 electron. That's why this bridge bond is 3 center, 4 electron bond. All these dimerization processes are a spontaneous process. Okay, the molecule gets dimerized on its own in order to gain the stability. Okay, done. One more example in this. We have ICl3, which dimerizes as I2Cl6. Okay, why this happens is that you see here. When you look at this ICl3, you can find out its geometry and hybridization. You'll get sp3d. This is TBP, trigonal bipyramidal. It has 3 bond pair and 2 lone pair. The hybridization is sp3d for ICl3. Now, because of its hybridization, the structure of ICl3 is this. Chlorine here, chlorine here, chlorine here. At this corner, we have one lone pair. At this corner, we have another lone pair. So this is the bonding we have. Trigonal bipyramidal. Okay. This is the lone pair of electron. Lone pair and lone pair. Okay. So here we have lone pair repulsion at this equatorial position. Now, when it dimerizes, shows three-centered, 4-electron bond. It dimerizes, and the structure will go like this. Sorry, ICLI. And the two lone pair, it is present over here. Now you see the two lone pair are placed at 180 degree to each other, and hence the repulsion reduces, and hence the stability increases. In fact, all these chlorine are going into the plane. All these are dotted line into the plane. And these chlorine atoms are coming out of the plane. Right, this is the structure we have. And most importantly is what? That these two lone pair now at 180 degree maximum distance, and hence the stability increases. And that's why it gets dimerizes. Right, so ICl3 converts into I2Cl6, BeCl2 converts into Be2Cl4, three-centered 4-electron bond. Done? Okay. Now the next one is back bonding. See, the back bonding, we have two types of back bonding. The first one is p-pi back bonding. You write it down, this p-pi back bonding. I'll explain why it is called p-pi back bonding. You'll understand it. Okay. First, we'll see this example here. p-pi back bonding is what? Suppose we have a molecule. We have a huge application of this, right? BF3 molecule, suppose we have. So BF3 molecule, you see, boron is bonded with 3 fluorine, trigonal planar structure we have. And in this bonding state, the boron has one vacant orbital that we know already. And each fluorine atom has 3 lone pair on. Boron has only 6 electrons. You see, this is the 6 electron has boron has. Okay. So because of this, electron deficient atom boron is. So what happens? Any fluorine, because all are the fluorine atoms only, any of this fluorine atom donates its lone pair of electron to the vacant orbital of boron. What is the benefit of it? The benefit is boron has 6 electron only in this state. When this fluorine atom donates its electron, it has 8 electrons. So it's octet complete. Right? So this is what the back bonding is. So what is happening here, you see, the boron and fluorine. Boron has vacant p orbital. Fluorine has lone pair present in p orbital. and this side we have again 2 fluorine atom present. It is possible with any one of the fluorine atom because all has the same size and same shape. So this lone pair, it donates into the vacant orbital of boron, and hence the octet of boron is complete. Right? So what happens here? This is p orbital, this is p orbital. So it is p overlap, we can say. p overlap. The bond that forms here, this bond has pi characteristics because this already has a sigma bond, right? Internuclear axis. This is lateral overlapping. So pi characteristics. Hence we call it as p pi. Why back bonding? Because sigma bond has already been formed and then this bond is forming, right? That's why it is p pi back bond. Understood? Tell me guys, it's clear? So p pi back bonding is possible when the two atoms belongs to the second period. This also belongs to the second period. This also belongs to the second period mostly. Mostly it happens in this case only. Back bonding it calls because one bond has already been formed, one sigma bond. Then fluorine is forming a bond again. After formation of a sigma bond, fluorine is donating, the molecule has been formed. And then the fluorine is donating its electron back to boron. Means when you draw the Lewis dot structure, will give electrons to fluorine. Fluorine donates its electron to boron. That's why it is back bonding. It forms after the formation of a sigma bond, after the molecule has been formed. That's why it is back bonding. Clear? Right, so in this what happens, you see, the electron deficiency, write down this point, the electron deficiency of boron atom decreases due to back bonding. The electron deficiency of boron atom decreases due to back bonding. Next line, as back bonding tendency increases, electron deficiency decreases. Right. So if you look at this molecule, one question they ask here, that compare the due to back bonding, the electron deficiency of boron decreases. As the back bonding tendency increases, yeah, this one line I said, na? 1 second. Due to back bonding, the electron deficiency of boron decreases. More back bonding or more tendency of back bonding, lesser will be the electron deficiency. More tendency of back bonding, lesser will be the tendency of electron deficiency. Lesser tendency of lesser will be the electron deficiency. Okay. Compare the Lewis acidity. Very important question. Compare the Lewis acidity of BF3, BCl3, BBr3, and BI3. See, Lewis acidity is what? Lewis acidity is the tendency to accept electron. Lewis acids are those compounds which has tendency to accept a pair of electron, right? Pair of electron. Now, all these boron are electron deficient. Okay. So, because of back bonding, what happens? The electron deficiency decreases. Electron deficiency decreases, then the molecule has less tendency to accept electron, and its Lewis acidity decreases. Correct. So if you look at this three molecule here, okay, in BF3, the boron has 2p orbital, fluorine has 2p orbital. Means 2p 2p overlap we have here. Here we have 2p 3p overlap, 2p for boron, 4p for bromine, 2p for boron, and 5p for iodine. What do you mean by this? See, when the orbital size is comparable, then the overlap is easy and the extent of overlapping is maximum here. But when the orbital size is not comparable, suppose it is 2p 2p overlap here. Suppose we have 2p 3p overlap is something like this. Right, so here the overlapping tendency is less because of the size difference. 2p 4p, again the size difference is large. Right, so it is 2p 3p, it is 2p 4p. So as the size difference increases, right, then the overlapping tendency decreases. Hence, in BF3 molecule, we have maximum tendency to overlap and forms the back bonding. Right? So back bonding tendency is maximum in BF3 and minimum in BI3. That's why the Lewis acidic behavior for these molecules is nothing but the tendency to accept electron. Bi3 is the most electron deficient molecule. Hence the order is this. Lewis acidic behavior. Yes, did you understand this? More, back bonding. Okay, fine. No problem. See, I'll explain this again, 1 second. See, actually, all these molecules have similar kind of bonding. For example, BF3, I'm writing it down, okay? BF3 is this. And boron has vacant orbital. When it has vacant orbital, so it behaves as Lewis acid. Behaves as Lewis acid. Why? Because since the vacant orbital is present, so it has tendency to accept electron. If you donate electron pair to this, it can accommodate the electron pair into this vacant orbital. That's why it is Lewis acid. Okay. So if it is electron deficient, it has more tendency to accept electron. But the electron deficiency decreases because of back bonding. Okay. So fluorine, what it does? Fluorine has the pair of electron, lone pair, right? So since the orbital size is also comparable, so it donates its electron to the vacant orbital of boron. Since it accepts electron from fluorine, so boron has less tendency to accept electron from any other molecule. Means its Lewis acidity decreases because of back bonding. Can we say that? All of you respond. Because of back bonding. Can we say that? Tell me. And what kind of back bonding is this? P-pi back bonding, right? Yes. So more the tendency to form a back bond, lesser, the behavior of this molecule, right? The Lewis acidic behavior is lesser, we can say, right? So if you look at BCl3 is this. This also has similar kind of bonding, but the only difference is the p orbital of boron and chlorine, we have a difference in size, because this is 2p and this is 3p. So more the size difference, lesser will be the tendency for back bonding. Hence what we can say, the back bonding tendency, p-pi back bonding tendency is maximum in BF3 and minimum in BI3. Would you agree with me on this? P-pi back bonding tendency is maximum in BF3 and minimum in BI3. Yes, is it clear? Respond, guys, all of you. Right? So maximum back bonding means minimum tendency to accept electron. Its Lewis acidity decreases. That's why I said that BF3 shows maximum back bonding. So its Lewis acidity is minimum, and BI3 shows minimum back bonding tendency. Its Lewis acidity is maximum. BF3, then we have BCl3, then we have BBr3, and then we have BI3. This is the Lewis acidic nature for the trihalides of boron. Clear? Yes. One important thing, this order I have given according to this p-pi back bonding must take care of that. Right. If you simply think of electronegativity, then you can say, sir, fluorine is the most electronegative atom. So it has the maximum tendency to accept electron. But that is not the case. Here we cannot take the factor as electronegativity. Electronegativity is not the factor here, not the major factor we can say. The major factor is p-pi back bonding. So according to electronegativity, if you write down the order will be exactly opposite. Right? According to p-pi, the order is this. So which factor dominates when? According to that only we'll write down the answer. So here you have to keep in mind, in case of BF3BCl3 means boron trihalide molecule, p-pi back bonding is dominating all other factors, and hence the Lewis acidic behavior is this. Any doubt? Correct. So fine, guys. So we have another type of back bonding here, which we call it as p-pi back bonding. Okay, and then we have odd electron molecules. Yes. Acidity, Lewis acidity, not acidity. I'm talking about Lewis acidity here, Shraddha. Okay, because the definition of Lewis acid is what? The molecule which has the tendency to accept a pair of electron is called Lewis acid. Right? So Bi3 is the most strong Lewis acid. BF3 is the least strong Lewis acid, or the weakest Lewis acid is BF3. Strongest one is Bi3. Clear? Any doubt? Yeah. So guys, next we have to start with p-pi and then odd electron bond. Okay, I won't start it today. We don't have time. Otherwise, I have to leave it in between. Okay, so we'll do this in next class. Half an hour mostly I'll take, and then we'll finish it off, and then we'll start with gases state. Okay, I have gone a bit fast today. Okay, so I request all of you to revise the entire session once. Okay, because we had to cover a lot since last class we missed. Right, that's why I've gone a bit fast. So all of you revise your notes. If you want, I will share the videos also with you later on. Okay. Anything else? Okay, guys. Thank you so much. Take care. Bye.